The first portraits were only the prologue, what happens when we watch a black hole in motion. I like questions that arrive like that simple at first glance, and then as you hold them up to the night they unfold. We have lived for a few short years with the astonishment of the first still photographs of event horizons. In the spring of 2019, the Event Horizon Telescope stitched the Earth into a single eye and revealed the shadow of the black hole in Messier 87, a dim disk of darkness wreathed by a ring of light at last. Made visible after a century of equations and hope, it was a portrait that felt like a chapter ending and a prologue. And then in the year 2022, we turned that same planetary eye toward home, the black hole at the center of the Milky Way Sagittarius. A star emerged, not as a static emblem, but as a living, changeable thing. Its glow shifts in minutes. Its silhouette is a shape that has to be inferred through motion. Even in those first reconstructions, you could sense it. The scene is not a photograph, so much as a single frame torn from a film we are only beginning to project. In 2024, we were given a new way to look by turning the light itself and reading its orientation. The Event Horizon Telescope released a polarized view of Sagittarius A star magnetic threads, traced around the shadow lines of order, arcing at the brink. The pattern echoed what we had seen around the black hole in Messier 87, hinting that near-horizon magnetic structure may be a common language spoken by gravity at its most extreme. It is, to my eyes, the first whisper of choreography, fields, and plasma, moving together 2 steps ahead of our cameras. So if the first portraits were prologue, the next decade is about movement. The phrase people use movies of black holes sounds like a metaphor, but it is not. The plan is precise. By adding more dishes to the network, by observing at multiple colors of radio light, by recording wider bandwidths, and synchronizing them with better clocks, the next generation Event Horizon Telescope intends to resolve not only the ring, but the ring in time, minute by minute, changes in the glow right at the edge of the abyss. We will not simply ask what a black hole looks like, we will ask how it behaves. Why now? Because the technology and the sky are meeting in the middle. Sagittarius A star is mercurial. It flickers on the timescale of a coffee break, not a career, which means you cannot understand it with a single still. You have to watch. Even the first scientific papers from the Event Horizon Telescope team emphasize this point. Most of the light at 1.3 millimeters arises from horizon scales, and it changes on the order of minutes to hours. The physics is dynamic, the instrument must be as well. And there is something else. We have already caught hints of the dance at shorter wavelengths. In the near-infrared, the gravity instrument at the Very Large Telescope Interferometer tracked glowing hotspots whipping round the black hole, their positions, and polarization looping in elegant arcs over tens of minutes. Those measurements, astonishing, delicate, suggest that flares come from bright knots in orbit, close to the innermost stable circular path threaded by strong magnetic fields. They are, if you like, the first rehearsal footage for the horizon-scale movie to come. To turn rehearsal into premiere, the array must grow. One of the most important additions is planned for the Southern Hemisphere, the Africa Millimeter Telescope in Namibia. It will fill a crucial gap in the global geometry of the array and sharpen our ability to track change, improving not just the crispness of the images, but the fidelity of time-resolved reconstructions. In simple terms, it helps the Earth-sized lens become more Earth-shaped and therefore more truthful moment to moment. The scientific reasons for a movie are as compelling as the romance. A film shows cause and effect. It lets you watch energy being drawn from the spin of a black hole and fed into a jet. It lets you see turbulence settle and reignite. It reveals whether the bright ring is a lighthouse beam sweeping with orbital motion or a more subtle interference of light paths. Multicolor imaging at roughly 86 GHz, 230 GHz and beyond will disambiguate layers of the flow jet base, brighter at longer wavelengths, inner accretion hotter at shorter ones. A time-resolved multi-frequency portrait is not a flourish. It is the instrument we need to test gravity where it is boldest. And so we return to the question, what happens when we watch a black hole in motion? Perhaps we will see the ring breathe, contracting and expanding as the feeding flow thickens and thins. Perhaps we will catch a bright knot born of magnetic reconnection shear as it orbits, leaving a faint wake we can follow, with algorithms designed to trace moving structure through noisy, incomplete data. Perhaps we will measure delays between colors that map the vertical spine of a jet frame by frame. All of this is specific, testable, and within reach of the instruments now being built and deployed. But beyond the list of metrics and models, there is the human answer motion turns an icon into a story. The still images were necessary. They changed the world. The films will do something different. They will teach us the tempo of the abyss. And once you know the tempo, you can begin to hear the music. I promised we would not stop at portraits. So let me show you in words how you make a film at the edge of a black hole. First, you enlarge the eye. You do not build a single gigantic mirror. You teach the Earth to act as one. Radio dishes scattered across the planet listen together their recordings, stamped by exquisitely steady atomic clocks and later combined, so that the separation between them becomes the lens. This is very long baseline interferometry, and at millimeter wavelengths, it gives you sharpness measured in tens of microarcseconds, fine enough to trace the glow close to the horizon. It sounds like a trick. It is really geometry and timekeeping. The telescopes hoard petabytes of data onto hard drives, then fly them to the correlators in Massachusetts and Bonn, where the signals are brought into phase and turned into something we can image. The clocks are hydrogen masers, the technique is Earth rotation aperture synthesis. The result is an Earth-sized telescope that in principle could pick out a tennis ball on the moon. That is the scale on which our story is drawn. Now, portraits become motion when you add two ingredients, time and color. The next generation Event Horizon telescope, an expanded, modernized array, has a singular aim not just sharper images, but time-resolved multicolor reconstructions of horizon-scale structure. The plan is to observe at several radio colors at once, around 86 GHz, 230 GHz, and higher, and to record with broader bandwidths so that minute by minute you can separate the bright inner flow from the jet base and watch how features move and fade. This is not a vague aspiration, it is the design brief. Color matters because nature is layered. Lower frequencies come on average from slightly larger, more extended regions. Higher frequencies see deeper toward the brink. If you observe them together and align their phases, each color offers a different slice of the flow. A technique called frequency phase transfer lets a more stable, lower frequency signal carry calibration up to less stable, higher frequencies, knitting the colors into a coherent film. In practice, adding an 85 to 86 GHz band significantly stabilizes and enriches the higher frequency movie, and it is especially helpful for the mercurial heart of our galaxy. Time matters because Sagittarius A star is restless. In 2024, we saw its magnetic fields traced directly in polarized light spirals and arcs wrapped around the shadow, implying ordered structure at the brink and the possibility of a faint jet. You cannot grasp such order in a single still. You must watch how those field-threaded filaments brighten, shift, and fade on the timescale of minutes. That is the promise of the coming decade, to see not only what the fields look like, but how they behave. To make that film, you also have to mend the lens. The black hole at the center of the Milky Way sits behind a turbulent scattering screen in the interstellar medium. At millimeter wavelengths, the blurring is reduced but not absent. It shifts, distorts, and adds a flicker that can masquerade as real change. Over the last few years, we have learned how to model and partly invert that scattering, treating it as a blur with a known anisotropic shape and a predictable, slowly varying wander, so that the underlying source can be recovered more faithfully. It is not magic, it is statistics and physics, and it will be crucial for honest movies. Then there is the choreography of the array itself. A film needs cameras placed at the right angles. Adding new dishes fills gaps in the virtual lens, improving not just spatial sharpness, but the fidelity of time-resolved reconstructions. One of the most strategic additions is planned for Namibia, the Africa Millimeter Telescope. It closes a continental hole in our geometry, strengthening north-south coverage and giving the global eye a steadier gaze on the southern sky. Beyond the science, it builds capacity and training on a continent that should be central to the next chapter. And behind the hardware sits a new kind of editing suite. Traditional imaging assumes a static source. That will not do for an object whose brightness pattern can change in the time it takes to make a cup of tea. New dynamical imaging algorithms embrace motion. They fit not a single picture, but a time-ordered sequence with gentle regularization that prefers continuity, yet allows orbiting knots, breathing crescents, and drifting filaments. Some approaches work directly with the robust closure quantities, sums of phases around triangles and ratios of amplitudes around quadrilaterals that survive station-based errors and atmospheric noise. Others select the moments during an observation when the evolving geometry of the array best supports time-resolved reconstruction. This is where computation meets choreography. If this sounds abstract, consider what the first trailers might reveal. A bright clump born in a burst of magnetic reconnection could shear and fade as it orbits near the innermost stable path. The ring's brightest segment might drift with orbital motion or pulse as turbulence waxes and wanes. Polarized light vectors could twist, coherently mapping field lines as they thread the plunge. With multiple colors recorded simultaneously, you could watch a disturbance propagate upward along a nascent jet longer wavelength, brightening first shorter wavelength response, later timing the journey and inferring the spine's speed and structure. Each of these is a specific testable signature in reach of the upgraded array. It is worth remembering that we are already halfway there. The method is proven. We know how to synchronize clocks across oceans, how to ship mountains of data by aeroplane, how to calibrate phases under restless skies, and how to turn incomplete, noisy measurements into reliable pictures. What changes in the next decade is scope, more stations, broader bandwidths, simultaneous colors, and algorithms built for motion. The prize is not merely a prettier image. It is the capacity to watch energy move at the edge of a gravitational well, to see cause and effect rather than infer them after the fact. The first pictures taught us that the shadow is real. The films will tell us how the darkness breathes. And when the first true sequences arrive, seconds stitched into minutes. Minutes into an orbit, I suspect we will feel something familiar. The portraits gave us presence. The movies will give us narrative. In the faint radio glow at the horizon, we will learn the timing of a faltering flare, the recurrence of a heartbeat in the plasma, the opening notes of a jet. We will not merely see a black hole, we will watch it act. I promised we'd make this a film, not a fresco. So let's step closer to the editing desk, to the place where motion becomes meaning. The first ingredient is rhythm, and the galactic center has it. Sagittarius A star, our home black hole, does not hold a pose. It flares and subsides on the scale of minutes to hours, which is precisely why a still portrait can only ever be a teaser. When we finally saw its shadow in the year 2022, the scientific notes that accompanied the image emphasized how quickly the brightness pattern morphs. The subject is alive on horizon scales. That is the invitation to make a movie. The 2024 follow-up taken in polarized light went further. It traced ordered magnetic fields right at the brink, a structure that begs to be watched as it twists and breathes in time. To capture that rhythm, you enlarge the orchestra. The Event Horizon Telescope, our planet-sized eye, began as a handful of observatories recording in unison. Over the years, it grew to include the Atacama Large Millimeter or Sub-Millimeter Array, phased to act as one exquisitely sensitive antenna, and the array has observed multiple seasons since 2017. Each new dish fills a gap in the Earth-sized lens. Each broader bandwidth sharpens both the image and the clock. The next decade raises the stakes again. The next generation Event Horizon Telescope is being designed explicitly to deliver time-resolved, multicolor sequences of the horizon, not just snapshots. Color here is not decoration but depth. At roughly 86 GHz, you are sensitive to a slightly larger, cooler envelope. At 230 GHz, you peer closer to the plunge. At 345 GHz, you aim almost straight at the rim. Observing these colors together lets you watch disturbances propagate through the flow, perhaps rising into a nascent jet or sinking toward the hole, so timing offsets between bands become a ruler for the engine. New calibration techniques such as frequency phase transfer let the steadier lower frequency signal carry a phase reference up to the higher, more skittish bands, effectively knitting the colors into one coherent film. There is also the sky itself to mend. Between us and the black hole lies a turbulent veil of ionized gas that blurs and jitters the view interstellar, scattering most famously along the line of sight to the galactic center. For years we treated that blur as a simple stretched Gaussian. More recent work builds physically motivated anisotropic models and even maps how the blur wanders and refracts with time. You can think of it as stabilizing a shaky lens. The better you model the shimmer, the more honestly you recover the true motion underneath. For Sagittarius A star, this is not a nicety, it is essential. The array's geography matters as much as its gadgets. One of the most strategic additions is planned for Namibia, the Africa Millimeter Telescope. Place a sensitive dish there, and the virtual Earth-sized lens fills a crucial hole, especially in north-south coverage of the southern sky. The result is not only crisper images, but more faithful frame-by-frame reconstructions, exactly what you need when your subject changes while the Earth turns. It is a scientific upgrade and a capacity-building project, anchoring frontier astronomy on a continent whose skies and students deserve a central role in the story. Now, to the editing suite, which is really mathematics. Traditional imaging assumes your target is static. That will not do for something that evolves in the time it takes to brew a cup of tea. Dynamical imaging treats the data as a time-ordered stream and solves not for a single picture, but for a gently regularized sequence that prefers continuity while allowing real motion, an orbiting knot, a drifting crescent, a breathing ring. Methods that work with closure quantities, those beautiful sums and ratios that cancel out many station-based errors, give robustness. Selective time-windowed reconstructions pick the moments when the array geometry best supports a clean frame. The result is not a guessy animation, but a statistically disciplined film. And we already have rehearsal footage at a different color. In the near-infrared, the gravity instrument at the Very Large Telescope Interferometer has tracked bright hotspots looping around the black hole over tens of minutes, with position and polarization tracing tidy arcs. A simple picture of a magnetized knot on a relativistic orbit explains those flares remarkably well. What we want now is to see the same choreography at the radio colors that outline the very rim where gravity's lensing sculpts the ring and the jet's footings may be laid. So what might the first true trailers look like? Imagine a flare born in a burst of magnetic reconnection near the innermost stable circular path. In the highest frequency band, the bright knot appears first. A heartbeat later, longer wavelengths brighten as the disturbance propagates outward along field lines. The ring's bright segment drifts with orbital motion, its polarization vectors sweeping like iron filings under a moving magnet. If a jet spine is present, we might time a pulse that climbs its length first, the longer wavelength band at the jet base, then the shorter wavelength band nearer the nozzle delays turning into speed. These are specific testable signatures the upgraded network is being architected to catch. And beyond the center of our own galaxy, there is the great archetype Messier 87. Its ring sits astride a relativistic jet we have known for more than a century at optical and radio wavelengths. New infrared views add further texture to that jet. Multi-band campaigns that pair horizon, scale radio imaging with shorter, wavelength monitoring will let us watch energy flow from the edge into the outflow. In a sense, Sagittarius A star gives us speed, Messier 87 gives us scale. Between them, the cinema of gravity will have both plot and panorama. All of this rests on a quiet miracle of logistics. Atomic clocks, hydrogen masers, keep time so faithfully that dishes separated by oceans can act as one. Hard drives the size of suitcases accumulate petabytes of night, then travel by aeroplane to central correlators, where the Earth's rotation becomes a gift, sweeping each baseline through new spatial frequencies and turning time into resolution. The Atacama Array's phasing system lets dozens of antennas hum as one, adding sensitivity that can make or break the fainter frames. It is patient, unshowy engineering, exactly the kind that makes a film hold together when the lights go down. If the first portraits were a revelation, the films will be a conversation. They will let us ask the black hole questions and watch it answer in real time. How does a flare grow? Where does a jet begin? When does magnetic order take hold? And when does turbulence tear it? And beneath those questions sits the old one that brought us here, a century-long curiosity, given a moving picture. What does gravity do to light at the very edge of no return? We're about to find out. I've often said that portraits change what we know, but films change how we know. So let me take you into the physics we can only reach once the pictures begin to move. When a ring of light breathes, it tells you where the energy lives. At the black hole in the Virgo giant Messier 87, the Event Horizon Telescope's ring has proved stubbornly consistent in size across seasons, an anchor for our understanding of gravity's lens at the brink. What has shifted is the way brightness drapes around that ring, the luminous crescent migrating, waxing, waning, as if the accretion flow were forever remixing itself. New observing epochs, strengthened by additional stations like the Greenland Telescope and the Northern Extended Millimeter Array, have underlined two truths. The diameter of the ring is steady, as general relativity predicts, and the glow upon it is alive, as turbulence demands. That combination geometry, fixed weather changeable, is precisely the canvas on which a time-resolved film makes sense. Now, when I say film, I do not mean a simple flipbook of images. I mean a measurement of causality. Imagine a flare near the innermost safe orbit, a pocket of plasma heated and brightened by magnetic reconnection. In a still image, it's a bright patch on a ring. In a sequence, you can watch it shear and drift with orbital motion. You can time how its brightness spills from one radio color to another, and you can trace whether any of that energy escapes upward into a jet. The Next Generation Event Horizon Telescope, an expanded array designed expressly for multicolour time-resolved imaging, exists to make that causal story legible, to give us minutes to hours sequences at roughly 130 GHz alongside sister bands lower and higher so we can separate the layers of the engine by their timing. There is a more delicate prize hiding in the ring's glow, the photon ring, a set of ever thinner subrings carved by light that orbits the hole 1, 2, 3 times before escaping. You won't simply draw these with a pen on paper. They reveal themselves as universal signatures in the interferometric data. On the longest baselines, a telltale ripple pattern, whose spacing and phase lock to the black hole's mass and spin. In other words, while the thick, bright ring paints the scene, the photon ring tunes the instrument. It offers precision tests of general relativity and a route to measuring spin that complements and chastens our models of the accretion flow. That too becomes clearer when time is a dimension in the data, not an inconvenience to be averaged out. To extract motion honestly, you need algorithms that assume change, not stasis. The imaging I grew up with treated the sky as a still life. The new methods are editors as much as painters regularized maximum likelihood reconstructions that solve for a sequence frame by frame, favoring gentle continuity while allowing genuine dynamics to break through an orbiting knot. Breathing crescent, a twisting polarization pattern. Some work directly with the robust closure quantities that survive atmospheric mischief. Others weave together multiple colors at once, stabilizing the higher skittish bands with phase references from the lower. It's mathematics turned into cinematography, and it is already built into the toolkits the collaboration uses. Hardware gives the tools their bite. The Atacama large millimeter or sub-millimeter array in the high Chilean desert doesn't just join the network, it phases dozens of dishes into one exquisitely sensitive ear. That beamformer is the quiet star of the present and the absolute necessity of the future, because sensitivity is time's best friend. When a source changes on the scale of minutes, you must hear everything you can in each heartbeat. Up north, new baselines from the Greenland telescope and other additions have strengthened the array's north-south reach, filling in the virtual Earth-sized lens, so that motion can be tracked without the frame tearing as the planet turns. Each new station is a new angle on the dance. And this isn't only a story about faraway giants. Our home black hole Sagittarius A star is the restless one, the one that flickers while you make a cup of tea. In 2024, the Event Horizon Telescope revealed its magnetic fields at the edge by rotating the light polarization as a fingerprint of order, and the pattern was strikingly similar to Messier 87's. That similarity hints at a common grammar of fields near horizons, whether or not a large jet is obvious to the eye, and it begs for time-resolved follow-up. Watch the vectors sweep. Catch the moment, order breaks and rebuilds. The only honest way to do that is as a film. Meanwhile, the great archetype in Virgo continues to connect scales. On human-sized nights, we watch the horizon glow. On longer campaigns, we trace the jet that spears out from the core. Multiband efforts now span from radio to infrared and beyond, with new facilities even resolving fresh structure in that legendary jet. Stitching horizon-scale radio frames to infrared and high-energy monitoring lets us ask, when the ring hiccups, does the jet answer? If we are lucky and persistent, we will be able to time the conversation. If all this sounds grand, remember that it rests on careful earthly craft. Hydrogen maser clocks keep time so steadily that dishes divided by oceans can listen as one. Suitcase-sized recorders swallow nights' worth of signal and carry them by aeroplane to correlators, where the Earth's rotation is not a nuisance, but a gift, sweeping every pair of telescopes through a rich set of spatial frequencies. And year by year, the array grows not only in hardware, but in reach projects like the Africa Millimeter Telescope in Namibia, closing gaps in the planet-sized lens, and just as importantly, opening doors for students and scientists who will tend this cinema for decades. So what does a film give us that a portrait cannot? It gives us arrows instead of dots, causes and consequences instead of mere co-locations. It lets us test whether the bright crescent drifts with orbital motion or is sculpted by a subtler interference of light paths. It times how quickly a disturbance climbs a jet's spine. It watches the choreography of magnetic fields as they bind and unbind the flow. And beneath all the jargon, it offers something very simple and very human. A chance to see the abyss not as an icon, but as a living system changing while we watch. That, I think, is worth the wait and the clocks and the frozen nights on mountaintops. Because once we know the tempo, we can begin to hear the music and perhaps for the first time dance in time with it. I want to listen for three kinds of timing in the abyss: the swift beat of orbits, the slower breath of the ring, and the cascading delays when energy climbs a jet or sinks toward the hole. We already glimpsed the first of these at shorter wavelengths. With the Very Large Telescope Interferometer, the Gravity team has watched compact, polarized hotspots sweep round the center of our galaxy on timescales of tens of minutes. Loops traced not only in position, but in the turning of the polarization angle, as if iron filings were following invisible field lines. Those near-infrared rehearsals tell us that the choreography is there to be filmed at the horizon itself, provided we can keep time with sufficient fidelity at radio colors. To do that, honestly, the new imaging tools must treat change as the default, not a nuisance. Traditional reconstructions built a single picture by averaging over an entire night, but a living source will not stand still for that portrait. The newer dynamical imaging methods solve for a gently regularized sequence, frame after frame, so that an orbiting knot, a drifting crescent, or a twisting polarization pattern can emerge without tearing the data apart. In some approaches, we reconstruct a video directly from the interferometer's measurements. In others, we locate time windows where the moving geometry of the Earth gives particularly clean snapshots and then stitch those together. It is mathematics turned into editing, and it is already present in the toolkits being developed around the collaboration. But time alone is not enough. We need depth, and in radio astronomy, depth comes from color. The next generation Event Horizon Telescope is being designed to record at the same moment bands near 86 GHz, 230 GHz, and when the weather smiles, even higher. The clever step is to let the steadier, lower frequency signal carry a phase reference up to the skittish higher bands, a technique called frequency phase transfer. In practice, adding an 85 to 86 GHz channel can stabilize the 230 and 345 GHz movies, extend coherence times dramatically, and widen the number of nights. When meaningful imaging is possible, that in turn means we can watch a disturbance appear first in the highest band near the rim, and then echo outward in the lower bands, turning color into a ruler for energy's path. Between us and the galactic center, however, lies a turbulent veil, the ionized interstellar medium, which blurs and jitters the view. At millimeter wavelengths, the worst of that blurring is reduced, but it is not gone. It wanders, stretches, and can masquerade as physical motion. Over the last decade, a framework nicknamed stochastic optics has matured a way to model the blur's deterministic average, while also accounting for its random refractive flicker, so that we may reconstruct both the true source, shimmering screen that sits in front of it. It is not a magician's reveal. It is physics and statistics, and it will be indispensable for time, resolved honesty towards Sagittarius A star. The instrument itself must grow not only smarter but wider. New stations fill holes in the virtual lens, especially in the north-south direction that matters for the southern sky. A pivotal addition is planned for Namibia, the Africa Millimeter Telescope on or near the Gamsberg. From that high plateau, a single dish links Africa into the global array, sharpening angular resolution and crucially for film improving frame-to-frame fidelity as the Earth turns. It is also a commitment to capacity on a continent whose students and skies should sit at the center of the next chapter. Recent funding news from the Netherlands confirms that this is moving from aspiration towards steel and concrete. All of this algorithms, colors, new sites converges on a simple question. Can we move from portraits to true horizon scale movies? The answer from Europe's Southern Observatory and from the Event Horizon Telescope's own communications has been unambiguous expansions over the next decade. With broader bandwidths, added telescopes and new observing frequencies are aimed squarely at high fidelity, time-resolved sequences of Sagittarius A star. They may even uncover a faint jet threaded by the magnetic order, already seen in polarized views. It is a plan with dates, designs, and a clear scientific target to watch cause and effect at the edge of no return. And then there is the finer prize hidden in the glow, the so-called photon ring. General relativity predicts an intricate stack of ever thinner subrings from light that loops once, twice, and more around the hole before escaping. You do not draw these with a pen, you detect their universal ripples in the interferometer's longest baselines where the visibility pattern betrays the ring's scale, and in some strategies the spin. Recent theory goes further, showing how to push beyond the idealized infinitely thin case toward the thicker real ring we observe. Here too, a sequence helps time, allows us to separate persistent universal signatures from the weather of the accretion flow riding on top. One day, to sharpen those signatures further, we may loft radio eyes above the atmosphere and extend baselines into space. Early studies suggest that Earth space, very long baselines, could resolve higher-order photon ring structure in a source like Messier 87 star and Titan tests of the Kerr description of a spinning black hole. Even orbit design becomes part of the craft chosen to tame the last shreds of interstellar scattering toward the galactic center. That is a longer road, but it is already being surveyed. For now, the near future is wonderfully grounded. We have a living target whose magnetic fields have been traced directly in polarized radio light. We have evidence from the near-infrared of compact knots that circle the brink. We have a design for simultaneous colors that turns weather into signal. We have a plan to mend the sky's shimmer, and we have a telescope rising on an African mountain to steady the planet-sized lens. The first portraits taught us that the shadow is real. The films will teach us how it behaves, how it brightens, fades, and hands energy from the ring to whatever spine of a jet may form. And as those minutes accumulate into orbits and orbits into seasons, we will at last trace not only the shape of gravity's edge, but its tempo. Then we will know the difference between a picture and a story. I want to be precise about what a movie buys us, because it is not only poetry, it is measurement. When we film the ring in time, we begin to time the engine. Minute by minute, we can watch where energy appears and where it goes, and the choreography we infer will be grounded in a plan. Already on the table, expand the Earth-sized eye, widen the recorded radio colors, and observe often enough to catch Sagittarius A star's quicksilver changes as they happen. In the spring of 2024, the collaboration made clear that this is the trajectory: new telescopes, larger bandwidths, new observing frequencies, and a deliberate march toward high-fidelity, time-resolved sequences. That same announcement showed magnetic order right at the rim in polarized light, making the case that there is a pattern to follow, if only we can keep up with it. The hardware blueprint has a name: the Next Generation Event Horizon Telescope. It is not a single mirror, but an upgraded network of radio dishes that together will deliver multicolor, time-resolved imaging on event horizon scales. The design papers describe an array built for minutes to hours cadence at multiple radio colors, so that we can separate the inner hotter flow from the jet base by their timing as well as their brightness. The ambition is plain real-time and time-lapse movies of supermassive black holes, showing both the steadfast geometry predicted by general relativity and the living weather of the accretion flow that rides upon it. Depth in radio astronomy comes from color, and color here means frequency. Add an observing band near 86 GHz, alongside the familiar 230, and when the sky allows 345 GHz, and you gain not only another layer of the flow, but a stabilizing reference. The clever technique is called frequency phase transfer. The steadier, lower frequency signal carries a phase reference upward to the skittish higher bands, effectively lengthening the time over which the array can stay in step. The result is sharper frames and more honest timing, even on nights when the air is less than perfect. This is not a hopeful guess. It is a quantified design choice argued in the technical literature for the next generation array. There is a veil between us and the galactic center, a shimmering screen of ionized gas that blurs and jitters the view. At millimeter wavelengths, the worst of that blur is softened, but it does not vanish. It wanders, stretches, refracts. Over the last few years, a framework has matured to deal with this, honestly modeling both the average anisotropic blur and its random refractive flicker, so that reconstructions can separate the true source from the sky's shimmer. It is sometimes nicknamed stochastic optics, and for Sagittarius A star, in whose direction the interstellar medium is particularly unruly, it will be indispensable for turning sequences into truth. A film also needs cameras in the right places. One of the most strategic additions is planned for Namibia, the Africa Millimeter Telescope, a 15-meter class dish on or near the Gamsberg that links Africa into the global network. Place a sensitive station there, and the virtual Earth-sized lens fills a crucial gap, especially in the north-south direction that matters for the southern sky. The project is now funded for construction with a mandate not only to sharpen the planet-wide eye, but to build capacity students, engineers, and scientists on the continent that hosts it. It is a scientific upgrade and an investment in people both necessary for the decade of movies ahead. Of course, images are made in software as much as in steel. Traditional reconstructions assumed a still life. The new dynamical imaging methods fit a sequence frame by frame, with gentle regularization that prefers continuity yet allows genuine motion, an orbiting knot, a breathing crescent, a twisting polarization pattern. And because the atmosphere and electronics can misbehave station by station, many approaches lean on the robust closure quantities, combinations of phases and amplitudes that cancel out local errors to stabilize the reconstruction. Recent work even explores fitting images directly to closure traces themselves, and experiments with learned priors are beginning to show how machine learning can help turn sparse, noisy measurements into films that are both expressive and disciplined. What will we time when the frames begin to flow? First, the swift beat of orbits. Near-infrared interferometry has already tracked compact polarized hotspots, circling the black hole over tens of minutes, with polarization angles looping like iron filings under a moving magnet. At horizon-scale radio colors, we expect to see related features that shear and drift with orbital motion, and because we will have several colors at once, we can measure the delays as disturbances rise into a jet or sink toward the hole. A brightening first at the highest frequency nearer the rim, followed by a response at lower frequencies further out, would be the clean signature of energy moving through the engine. Second, we will time the breadth of the ring. In Messier 87, the diameter of the ring has remained steady across observing seasons as general relativity demands, while the brightness around it shifts with the weather of the flow. A movie lets us distinguish a lighthouse-like drift of the brightest segment, consistent with orbital motion from a subtler interference of light paths that could fix the hotspot without motion. The next generation array is engineered to make that distinction in minutes, not years, by delivering multicolor cadence fast enough to watch causes and consequences unfold. Third, we will hunt for the photon ring's signature, the nested subrings carved by light that orbits the hole 1, 2, 3 times before escaping. You do not etch these as thin lines. You hear them in the longest baselines as a universal ripple pattern in the interferometric data, whose spacing and phase encode the black hole's mass and spin. Time helps here as well. By averaging intelligently over sequences, we can tease out the persistent, geometry-driven signal beneath the flicker of the flow-tightening tests of the spinning black hole description without pretending source is static. All of this rests on a rhythm of observing that is at heart remarkably human. Choose a window when the weather and the clocks are kind point, the planet-sized eye, and listen together. Since 2017, the collaboration has gathered multiple campaigns, and 2024 brought another with the explicit aim of improving images year by year as new stations, wider bandwidths, and fresh frequencies come online. The first portraits were declarations. The next decade's campaigns are designed as conversations each season, adding a line to the dialogue until the ring is not only seen but watched. And I think that is why this enterprise feels so alive. We have a target whose magnetic fields have now been traced right at the brink, a blueprint for an expanded multicolor time, resolved array, techniques to tame the shimmer of the interstellar medium, an African dish rising to steady the Earth-sized lens, and an observing cadence tuned to a source that changes while you make a cup of tea. The portraits prove that the shadow is real. The films will tell us how it behaves, how it brightens, fades, and hands energy from the ring to whatever spine of a jet may form. In learning that tempo, we will move from an icon to a story, and from a story to a science that unfolds while we listen. I want the next chapter to feel like rushes arriving from a night on the mountain, frames you can hold up to the light and hear the engines timing in them. First, cadence. If portraits taught us patience, movies will demand agility. The collaboration is actively building toward that, not only more dishes and broader bandwidths, but observing that can happen more frequently and more flexibly with hardware-software pipelines designed to catch changes as they unfold. You can already see this philosophy in the so-called agility work, automating more of the setup, shortening the path from weather, window, to recorded sky. Because a black hole like Sagittarius A star changes on the scale of a tea break, not a season. The point is simple: if you want a film, you must be able to roll on short notice, often, and in multiple colors at once. Second, narrative clues are multiplying on the Virgo stage. New analyses comparing magnetic field maps of the black hole in Messier 87 across several campaigns show that the orientation of the polarized pattern can change dramatically from year to year, spiraling one way, settling then reversing, while the ring's size remains stubbornly consistent with gravity's geometry. In other words, the set is the same, the weather is not. That is precisely what a film is for, because it replaces the question, what does it look like, with what changes first, and why third rehearsal footage already exists at a different color. In the near-infrared, the gravity instrument has tracked compact, polarized hotspots arcing around Sagittarius A star over tens of minutes. More recently, teams have even performed orbital polarimetric tomography, reconstructing the three-dimensional dance of a flare from its changing brightness and polarization. Those results strengthen a simple picture: brief magnetized knots of plasma orbit near the innermost stable path, and then dissipate likely in episodes of magnetic reconnection. Our aim now is to watch the same choreography right at the radio colors of the rim. But a film is edited as much as it is shot, and new algorithms are the editors. Classical imaging assumed the sky would hold still while the Earth turned. It will not. Selective and dynamical imaging methods now solve not for a single portrait, but for a gently regularized sequence of frames, trusting continuity while allowing real motion, an orbiting knot, a breathing crescent, a twisting polarization, pattern to break through. Some approaches even choose the cleanest beats during an observation, stitching together those windows when the moving geometry of the array best supports crisp frames. The spirit is cinematic. Prefer coherence. Never mistake noise for action, and let physics dictate the cut. Depth in radio light comes from color. The next generation Event Horizon telescope aims to record multiple radio colors simultaneously, not only the familiar 230 GHz band, but also a lower band near 86 GHz, and when the sky allows, higher still. The clever trick is called frequency phase transfer. Let the steadier lower frequency signal carry a phase reference up to the skittish higher band, effectively lengthening the time the global eye can stay in step. In practice, adding that lower band can transform the stability, cadence, and astrometric honesty of horizon-scale movies, especially for the mercurial heart of our galaxy. Between us and the galactic center lies a shimmering veil, the ionized interstellar medium that blurs and jitters the view. You cannot wish it away, you must model it. A framework nicknamed stochastic optics treats the blur as both a deterministic average and a random refractive flicker, so reconstructions can separate the true source from the sky's shimmer. For Sagittarius A*, this honesty will be indispensable because the line of sight is notoriously unruly, even at millimeter wavelengths. Movies must be faithful to motion on the horizon, not the atmosphere between. Geography is part of cinematography. To keep the planet-sized lens steady on southern targets, a missing tile must be placed on the African continent. That is the role of the Africa Millimeter Telescope in Namibia, a 15-meter class dish on or near Gamsberg that fills a crucial north-south gap in the virtual aperture, improving not only sharpness, but the honesty of frame-to-frame reconstructions as the Earth turns. It is also an investment in people and place funding, training, and a pipeline of students who will tend this cinema for decades. All of this only matters because the targets keep giving us something to time. Consider a clean, testable scenario for the first trailers. A knot brightens near the inner rim, perhaps ignited by magnetic reconnection. In the highest frequency band nearest the brink, you see it first. Moments later, lower frequency bands respond as the disturbance propagates outward along field lines. If a jet spine is present, a pulse marches upward, longer wavelength brightening at the base, followed by shorter wavelength response closer to the nozzle. The delays become a ruler. The ruler becomes speed and structure. The same sequence watched in polarized light would show vectors sweeping and reordering as the fields bind and unbind. That is not a poetic flourish. It is the observational strategy now being designed into the instrument. And the Virgo giant continues to anchor our sense of scale. New campaigns with improved baselines have tightened the ring's size, while revealing year-to-year changes in polarization and azimuthal brightness weather draped on immutable geometry. Parallel multi-wavelength programs from radio through infrared and high energy are beginning to trace how horizon-scale changes converse with the famous parsecant-long jet. The ambition is straightforward: when the ring hiccups, time the echo down the outflow. A film is exactly that: cause on one frame, consequence on the next. And finally, a word about resolution, because the urge to sharpen never leaves us. The collaboration has pushed its longest Earth-spanning baselines to their limits and is adding higher frequency capability. But the most delicate universal signatures, the thin photon ring ripples set by gravity alone, may demand both exquisite coverage and one-day baselines that reach beyond Earth. Theory tells us those subrings leave a telltale pattern in the interferometer's data on the very longest spacings. Time-aware analyses can help tease the persistent geometry from the flicker of the flow. Whether we stay on the ground or reach higher, the principle is the same. Let gravity set the meter and let the movie keep time. So when I say movies of the abyss, I mean exactly that. Not a metaphor, but a plan. Faster, more frequent observing. multicolour eyes knit together by clever calibration, algorithms that assume change, a mended sky, a new dish rising on an African mountain, and a cadence tuned to a source that changes while you make tea. The portraits were the prologue. The horizons caught in motion minute by minute are the story. I want to linger on what time resolve really means when your subject is gravity itself. Because once you keep time faithfully at the brink, every delay becomes a ruler, every drift becomes a compass. You begin with a promise the community made in the spring of 2024 that the Event Horizon Telescope would not only repeat its observing campaigns, but expand them more stations, larger bandwidth, new observing, colours explicitly to deliver high-fidelity, horizon-scale movies. The polarised portrait of Sagittarius A star, released that March, was not just a picture, it was a statement of intent. Magnetic order is present at the edge, so let us watch it breathe. The Next Generation Event Horizon Telescope, an expanded network sometimes called ONGI-EHT, is the instrument designed for that intent. Its brief is clear tri-band near simultaneous observations around roughly 86, 230 and 345 GHz, wider per station recording rates, and added dishes at new long baselines to harden both spatial detail and timing. In plain terms, a planet-sized eye that sees several radio colours at once and fast enough to follow a flare as it grows shears and fades. Colour is depth in radio astronomy, and synchronizing colours is the clever step. A technique called frequency phase transfer lets a steadier lower frequency band carry a phase reference up to the higher, more skittish band. Add a band near 85 to 86 GHz to the familiar 230 and 345, and the array can stay in step for longer, yielding sharper frames and more honest timing on nights that would otherwise be marginal. That is not wishful thinking, it is an argued design choice in the technical literature for the next generation array. Between us and the galactic centre lies a shimmering veil ionized gas that blurs and jitters the view. You cannot average that shimmer away when you are making a film, you must model it. A framework nicknamed stochastic optics treats scattering as both a deterministic blur and a random refractive flicker, allowing reconstructions to separate the true source from the sky's wander. For Sagittarius A, star whose line of sight is notoriously unruly, that honesty is indispensable if a sequence is to reflect motion on the horizon rather than the atmosphere in between. Cameras, of course, must be in the right places. A missing tile in our virtual lens sits on the African continent, and that is precisely what the African Millimeter Telescope in Namibia is meant to supply. A 15-metre class dish on or near the Gamsberg Plateau fills a crucial north-south gap for southern targets, improving not only angular sharpness, but the fidelity of frame-to-frame reconstructions as the Earth turns. The project is now funded by European partners specifically to enable colour movies of black holes, and it doubles as an investment in training and local capacity for the next decade of horizon cinematography. And then there is the editing suite, which is mathematics. Classical imaging assumed the sky would hold still. It does not. Dynamical imaging methods now solve not for a single portrait, but for a gently regularized sequence, trusting continuity while allowing real motion to break through. Many approaches work directly with the robust closure quantities, combinations of phases and amplitudes that cancel local errors, so an orbiting knot, a breathing crescent, or a twisting polarization pattern can emerge without being mistaken. For calibration, it is computation as cinematography. What then do we time? First, the swift beat of orbits. Near-infrared interferometry has already tracked compact polarized hotspots circling Sagittarius A star over tens of minutes, with the polarization angle looping like iron filings under a moving magnet. Those results are now so mature that teams perform orbital polarimetric tomography, recovering three-dimensional structure from how brightness and polarization change. They are rehearsal footage telling us that the choreography is there to be filmed at the rim in radio light. Second, the slower breath of the ring. In Messier 87, the diameter of the bright ring has remained stubbornly steady across seasons, general relativity's geometry holding firm, while the brightness around it shifts with the weather of the flow. New epochs with longer baselines and higher frequency capability have tightened that picture and made a simple, practical point, fixed geometry, lively weather, is exactly what a time-resolved multicolour film is for. Third, the conversation with the jet. Horizon scale changes should, if we are fortunate and persistent, echo along any outflow. That conversation is now visible across wavelengths. The first black hole we imaged at the heart of Messier 87 carries a celebrated jet, Fresh infrared views have begun to deepen that picture, while radio campaigns continue to resolve its structure from the core outward. Stitched together horizon frames and jet monitoring turn a film into causality when the ring hiccups time the answer down the spine. There is a subtler prize hiding in the glow, the photon ring, the nested subrings carved by light that loops around the hole 1, 2, 3 times before escaping. You do not etch those subrings as lines. You hear them in the interferometer's longest baselines, as universal ripples in the data whose spacing and phase encode mass and spin. Recent theory shows how to push beyond the ideal, infinitely thin case to the thicker real rings we observe, crucial if we want to extract geometry cleanly beneath the flicker of the flow. Time helps here too, average wisely across a sequence, and the persistent geometry rises above the weather. Add these pieces together, and a simple, testable scenario for the first trailers emerges. A knot brightens near the inner rim, perhaps born of magnetic reconnection. At the highest frequency, nearer the brink, you see it first. Moments later, lower frequency bands respond as the disturbance propagates outward along field lines. In polarized light, the vectors sweep and reorder as magnetic structure binds and relaxes. If a jet spine is present, a pulse marches upward, a longer wavelength, brightening at the base, followed by shorter wavelength response closer to the nozzle. The delays become a ruler. The ruler becomes speed and structure. That is not a flourish. It is the observational strategy now being engineered into the instrument. And beneath the engineering sits something very human. The first portraits gave us presence. The movies give us narrative. In the faint radio light at the edge of no return, we will time the engine watch, energy appear, move, and sometimes escape into the wider galaxy. We will not merely see a black hole. We will watch it act minute by minute, color by color, until gravity's silence acquires a tempo we can name. I keep coming back to the thought that a black hole only truly reveals itself when you keep time with it, when you let the clock set by gravity become your metronome. And lately the universe has started to play in time. On the Virgo stage, the ring around the giant in Messier 87 refuses to change its size, yet the magnetic weather dancing across it has flipped and swung over the years, spiraling one way, settling then, reversing like a conductor changing the baton's hand mid-movement. That is the promise of cinema at the horizon. The geometry holds the score as in the dynamics. The Event Horizon Telescope's new polarized images across 2017, 2018 and 2021 make that point with exquisite clarity. The ring persists, but the field lines tell a different story. Each season, closer to home at the heart of the Milky Way, we have now seen the glow of Sagittarius, a star threaded by strong, organized magnetic fields revealed in polarized radio light for the first time. What struck many of us is how similar that structure is to the Virgo. Giants, a hint that magnetic order at the brink could be a common refrain in supermassive engines. And while the center of our galaxy has not yet shown a clear jet at these radio colors, that ordered field whispers that one may be there waiting to be caught in the right light or at the right moment. If portraits taught patience, movies demand agility and palette. The next generation Event Horizon Telescope, an expanded global array, leans into both. Its blueprint calls for tri-band near simultaneous, observing around roughly 86, 230 and 345 gigahertz. More dishes to stitch longer and more numerous baselines, and per station recording rates beyond 250, 6 gigabits per second to catch faint fast structure. The aim is straightforward: watch a flare form, shear and fade, while holding focus across colors that each peer to a slightly different depth. Synchronizing those colors is the clever step. A technique called frequency phase transfer lets a steadier lower frequency channel carry the phase up to a skittish higher band, taming the atmosphere long enough to make the higher color frames usable. Reviews over the last few years argue this approach could be transformative at 345 gigahertz. Practical demonstrations now report that the method is working on the very longest Earth-sized baselines, opening the door to true multicolour, time-resolved imaging of the brink. Between us and the galactic centre lies a restless veil, the ionized interstellar medium that blurs and warps the picture. You cannot average that away when your subject changes minute by minute. You must model it as it lives. A framework nicknamed stochastic optics does exactly that, separating a deterministic time-average blur from the random refractive flicker so we can disentangle horizon-scale motion from the shimmer of the path. For Sagittarius, a star notorious for unruly scattering, this honesty is not optional. It is how a movie remains a movie. The rehearsal footage in a different color already exists. In the near-infrared, the gravity instrument has watched compact polarized hotspots loop around Sagittarius A star on timescales of tens of minutes, the polarization angle wheeling like iron filings under a bar magnet. More recently, orbital polarimetric tomography, an elegant mouthful, has reconstructed the three-dimensional dance of a flare from its changing brightness and polarization alone. Take those same dynamics, and you have the storyboard for radio light cinema at the rim. And beyond the ring, the conversation continues down the spine of a jet. Fresh infrared eyes have joined the orchestra. The James Webb Space Telescope has now resolved the Messier 87 jet in the near-infrared, with new clarity even catching a faint counterjet. That matters for timing. If the ring hiccups and a pulse marches outward, multicolor monitoring from horizon to outflow can turn delays into a ruler for speed collimation and field geometry. Of course, a film is edited as much as it is shot. The algorithms have changed their assumptions, no longer a still sky stitched over hours, but a gently regularized sequence in which continuity is trusted and genuine action is allowed to break through. Some methods work directly with closure quantities, those combinations of phases and amplitudes that shrug off calibration errors so an orbiting knot or a breathing crescent can emerge without being mistaken for a bad game. In the long run, even more abstract closure traces may become part of the editor's toolkit because the goal is simple: prefer coherence without mistaking noise for narrative. And then there is the most delicate motif in the score, the photon ring. Theory tells us that light, which loops the black hole 1, 2, 3 times, etches a nested, nearly universal pattern, not just as a picture, but as ripples in the interferometer's longest baselines. Recent work pushes beyond the idealized, infinitely thin case to the thicker rings we actually observe, showing how the visibility pattern shifts when the ring has width. Paired with time-aware analyses, those signatures promise a way to let the persistent geometry sing above the weather of the flow. The craft that makes this possible is in its way as beautiful as the light itself. Atacama's great millimeter array is phased into a single giant eye, so the global network gains an anchor of sensitivity. Hydrogen, maser clocks, keep the far-flung stations in step, and the raw torrent of bits, hundreds of terabytes per telescope per day, flows to correlators that turn geography into resolution. In the next decade, we will add stations, open higher colors, and run faster pipelines, not to make prettier portraits, but to capture the black hole as it acts. That is the point of a film. So here is the scene I want to shoot. A knot of plasma brightens near the inner rim, born perhaps of magnetic reconnection, where field lines snap and rejoin. At the highest color nearest the brink, you see it first. Moments later, the lower color responds as the disturbance walks out along the field. In polarized light, the vectors sweep and reorder. If a spine exists, a pulse climbs the jet longer, wavelength brightening at the base, followed by the higher color echo further up. The delays become a ruler, the ruler becomes speed, structure, and field. The portraits were our prologue, the movie is the story we came to tell. I want to bring you into the control room, on a night when the abyss is not just seen but timed, when the ring is a clock face, and the magnetic field is the second hand you can watch sweep. We learned only recently that the heart of our own galaxy wears its fields, like ordered threads. In the spring of 2024, the Event Horizon Telescope turned its polarized gaze on Sagittarius A star and revealed strong, organized magnetic structure wrapped right at the brink. It is the same language we first read around the giant in Virgo Messier 87 geometry that holds and weather magnetic weather that dances. That single result did two things at once. It turned a portrait into a promise, and it told us the promise would be kept if we could keep time. Keeping time at the horizon requires an instrument written for motion. The blueprint already has a name: the Next Generation Event Horizon Telescope. It is not a single dish, but a choreography of many designed explicitly to deliver multicolor, time-resolved images on horizon scales. The plan is clear. In the design work, observe at 3 radio colors together near 86, 230 and 345 gigahertz, while expanding the number and placement of stations so that minute by minute the global lens stays honest as the Earth turns. In plain words, we will not only sharpen the ring, we will watch it act. Synchronizing those colors is the clever step that makes a film possible on nights when the air is less than kind. A technique called frequency phase transfer lets a steadier lower frequency channel carry a phase reference up to the skittish higher band. The calibration becomes a bridge. Coherence lasts longer. Frames become sharper. This is not wishful thinking. There is a growing literature setting out exactly how frequency phase transfer transforms high-frequency, very long baseline interferometry. And the next generation array has incorporated it as a design choice. In fact, teams now report successful demonstrations and pathways to deploy it across observatories that already join the Event Horizon Telescope. There is between us and the galactic center a restless veil ionized gas that blurs and jitters the view. When you are making a movie, you cannot simply average that shimmer away. You must model it as it lives. A framework nicknamed stochastic optics does exactly that, separating a deterministic anisotropic blur from the random refractive flicker, so that time-resolved reconstructions can tell the difference between motion on the horizon, shimmer in the sky. For Sagittarius A star, whose line of sight is notoriously unruly, the honesty is not a flourish, it is fidelity. A film also needs its cameras in the right places. The virtual Earth-sized lens has had a missing tile on the African continent, and that is the role of the Africa Millimeter Telescope on the Gamsberg Plateau in Namibia. Put a sensitive 15-meter class dish there, and you fill a crucial north-south gap for southern targets, improving not only angular sharpness, but the frame-to-frame truthfulness of time-resolved reconstructions. The project is more than a dot on a map. It is a funded international effort with a mandate that explicitly includes color, movies of black holes, and the training of the students who will make them. What then will we time begin with the swift beat of orbits? In the near-infrared, the gravity instrument has already watched compact polarized hotspots sweep around Sagittarius A star on timescales of tens of minutes. More recently, teams have used orbital polarimetric tomography to reconstruct the three-dimensional dance of a flare, evidence that the choreography exists to be filmed at radio colors right at the rim. The translation is straightforward. If a knot brightens first at the highest radio color and then echoes to the lower band, the delay becomes a ruler for energy's path through the engine. On the Virgo stage, the ring has taught us a different lesson: geometry, fixed weather, changeable. Multi-year campaigns show a ring whose size stays stubbornly consistent with gravity's lens, but whose polarized pattern can flip and settle and flip again. Magnetic order, rearranging itself over seasons while the silhouette holds. That is exactly what a movie is for, because a sequence lets us ask not what does it look like, but what changes first and why. There is also a more delicate motif hidden in the glow, the so-called photon ring, the nested sub-rings etched by light that loops the hole once, twice, thrice before it escapes. You do not sketch these as thin lines, you hear them as universal ripples on the longest interferometric baselines. Theory has shown how those signatures encode the mass and spin, and more recent work goes beyond the idealized infinitely thin ring to the thicker real rings. We will actually measure exactly the kind of detail a time-aware analysis can help to reveal by letting persistent geometry rise above the flicker of the flow. And beyond the ring lies the conversation with the jet. Here the orchestra has gained a new instrument. The James Webb Space Telescope has delivered the sharpest infrared view yet of the Messier 87 jet, even tracing a faint counterjet. Stitch that kind of outflow mapping to horizon-scale radio sequences, and you acquire causality when the ring hiccups time the echo down the spine. Let delays become speed, and speed become structure. All of this rests quietly on engineering that feels almost musical. Hydrogen maser clocks keep far-flung dishes in step. Phased arrays like the great Atacama interferometer lend the sensitivity that buys you minutes, scale cadence. Hard drives swallow nights of sky and carry them by aeroplane to correlators, where the planet's rotation turns time into resolution. The designs for the next decade are explicit, more stations, higher recording rates, simultaneous colors and algorithms that assume change rather than punish it, so that we can not only see a black hole but watch it act. So imagine the first true trailer. A bright knot born in magnetic reconnection flares near the inner rim. At the highest color nearest the brink, you see it first. A heartbeat later, the lower color responds as the disturbance walks out along the field. In polarized light, the vectors sweep and reorder. If a spine exists, a pulse climbs the jet longer, wavelength brightening at the base followed by a shorter wavelength echo further up. On the longest baselines, a quiet ripple persists beneath the weather, the photon ring signature geometry's metronome holding the tempo while the music plays. That is what a movie buys you: arrows instead of dots, causes and consequences rather than co-locations, the difference between an icon and a living system. And that, I think, is why we came to learn the tempo of the abyss.